Okay, my dear student, let us continue the sequence class. Here today I would like to prove four theorems. So based on the convergent sequence. If two sequences are convergent, plus is also convergent, minus is also convergent, multiplication is also convergent, division is also convergent, that I would like to prove. Among those, the first one is if an and bn are convergent sequences and converges to a and b respectively, a is convergence to a, bn is convergence to b, then prove that an plus bn is also convergent and converges to a plus b. Or in other words, suppose the sequence an as n tending to infinity equal to a and the sequence bn as n tending to infinity equal to b, then prove that limit an plus bn as n tending to infinity is a plus b. Okay, an is a convergent and converges to a. Therefore, according to definition of the convergent, limit is a. If you remove this limit definition or use the definition of a limit, so for a given epsilon there exists n1 such that mod of an minus a is less than epsilon by 2. You are free to select any number here. I have chosen epsilon by 2 just to get epsilon at the end. So just you are free to, even you can select epsilon by 3, epsilon by 4, epsilon by 8, epsilon by any number. Epsilon itself is a small number, epsilon by 2 is still a smaller number. Therefore, you are free to choose. So I have chosen particularly epsilon by 2 just to get final answer epsilon. So Bn is also convergent and converges to B, and limit Bn as n tending to infinity equal to B. Again, for given epsilon, there exists n2 such that Bn minus B is less than epsilon by 2 for all n greater than or equal to n2. So as n is greater than these two number, among these two or between these two, if m is a maximum, maybe n1 maximum or n2 maximum, let us take between these two, one number is maximum, I will take that maximum number, the bigger number, m is the maximum of n1 and n2. So then consider this an plus bn minus of a plus b equal to, rearrange it, an minus a plus bn minus b. You split this, then modulus sign says less than or equal to an minus a plus bn minus b. So by definition of the modulus, and an minus a, from that definition of the an, it is epsilon by 2. So in the equation number 1, and bn minus b is also less than epsilon by 2 for all n greater than or equal to m, maximum of n1 and n2. So for that, an plus bn minus a plus b is less than epsilon. So this is a limit. Therefore, limit an plus bn as n tending to infinity equal to a plus b. Therefore, an plus bn is convergent. On the similar line, if you try this, an and bn are convergent, converges to a and b respectively, then I have to prove, or we have to prove, an minus bn is also convergent and converges to a minus b. Or in other words, an limit as n tending to infinity equal to a and limit bn as n tending to infinity equal to b, then we have to prove limit an minus bn as n tending to infinity equal to a minus b. You try, just replace the plus by minus sign in the above theorem. You definitely will get, the remaining conditions are same, just replace plus by minus, definitely you will get this. If you don't get, you ask me, will true, we can prove in the next class. Okay, the next theorem is, as an and bn are convergent and converges to a and b respectively, then prove that an into bn is also convergent and converges to a into b. Or in other words, limit an as n tending to infinity equal to a and limit bn as n tending to infinity equal to b, then prove that an into bn as n tending to infinity equal to a into b. Okay, in the proof, an is a convergent and converges to a. As usual, the definition of the limit an as n tending to infinity equal to a. Therefore, for given epsilon, there exists n1 belongs to the natural number such that an minus a less than, just right here epsilon by 2. We'll see how much I have written m2 here. We'll see why this m2 comes here. We'll write it at the end. So why it is m2? See, let us call this equation number 1 for all n greater than or equal to n1. So we have to, why this is particularly m2, we'll see at the end. So an is convergent, therefore it is bounded, because we have proved a theorem, every convergent sequence is a bounded sequence. Therefore an less than or equal to m1 for all n. Similarly, bn is convergent and converges to b. So Bn limit as n tending to infinity equal to b for given epsilon positive, there exists n2, so belongs to natural number such that Bn minus b less than, you just write epsilon by 2. We'll see at the end again why this modulus of a. You can understand at the end. So why I have written this is a modulus of a. So for all n greater than or equal to n2, this is the equation number 3. So Bn is convergent, again it is a bounded, so Bn, modulus of Bn less than or equal to m2 for all n. It is the upper bound definition. Here also it is the upper bound definition. Now for a maximum, m is a maximum of n1, n2. Then consider modulus of an, bn minus ab. So an, bn minus, subtract and add bn into a plus bn into a minus ab. An, bn minus ab as it is, minus plus, just the term is add and subtract here. So then separate this an, bn minus bn plus bn a minus ab. So this is less than or equal to these two modulus sign. So modulus of bn is outside. So mod of an minus a plus mod of a is taken, it means modulus of a into mod of bn minus a. So this modulus of bn, according to definition of the sequence boundedness, it every bn is less than or equal to m2. Therefore I have written m2 here. So this an minus a, I have chosen it is less than epsilon by 2. That is why I have written there divide by m2, just to cancel this m2, getting only epsilon by 2. So this m2 is chosen there just to cancel this m2. So anyhow you are free to select this epsilon term. It is a very small number. You are free to select this number. According to your choice you can take it. So modulus of a, bn minus a. I have chosen there bn minus a is less than epsilon divided by mod of a. This just to cancel this mod a, get only epsilon by 2. Just to get epsilon by 2 plus epsilon 2, I have chosen these two numbers there. So you are free to select it. Then epsilon by 2 plus epsilon by 2 is epsilon an, bn minus ab. So again definition of the limit says an, bn equal to ab as n tending to infinity. Therefore it is convergent. So note one more thing here, student. Instead of subtracting and adding bn into a, you are free to select an into b. Add and subtract an into b, an into b. So you are free to select. In that case an will be common. If you take an, m1 will come here. m1 is the term here. Then you have to select that an minus bm as, so bn minus a, b you are getting here. bn minus b you are getting, that is epsilon by 2. m1 you have to select. So here mod b will come and an minus a will come there. So in that case you have to select, so epsilon divided by 2 times mod of b to cancel this mod b. Instead of this, if you select different, means an into b, if you select it, you will get that. So you try, using that you try this. Okay, so this is an into bn is convergent and converges to ab. So theorem an is a convergent and converges to A, Bn is a convergent and converges to B, then we have to prove that An by Bn is also convergent, converges to A by B, or limit An by Bn as n tends to infinity is A by B. Okay, so let us see this. An is convergent, use the definition, epsilon divided by 2. Why this m2 we'll see later, as we have done in the previous theorem. So An is convergent, definitely it is a bounded. So An is less than or equal to m1 for all n. So Bn is convergent and converges to B means the limit says. So as you have done in the previous theorem, same thing. So only thing here I have to select that it is a bounded. It is a bounded means epsilon divided by mod of B into m2 divided by 2a. Just you write epsilon by 2. Why these two numbers we'll see later. According, we have to adjust this term at the end. So those terms we have to write here. Anyhow, it is a epsilon term, very small number. It is a small. This is adjustment term. Even this is also adjustment term. So this m2 comes extra. This is how we'll see at the end. So Bn is a convergent, therefore it is a bounded. Definitely, bounded means it is both upper and lower bound. So particularly I have chosen lower bound. Why this is lower bound? You come to know this is. So modulus of Bn greater than or equal to small m2 for all n, and you get the reciprocal of this 1 upon Bn is less than or equal to 1 upon m2. So greater Bn greater becomes smaller when I take the reciprocal. So the inequality changes. So this is very important part in this theorem. So consider for a maximum of n1 and n2, an upon bn minus a by b equal to, get the LCM bn into b, cross multiply an into b minus bn into a. So an into b minus bn into a divided by bn into b. So separate that modulus sign. So for this, add and subtract minus ab and plus ab. Minus ab and plus ab, this term I have to take it. So then separate that modulus. ANB minus AB plus AB minus BNA. Here in the numerator, B is a common term. So to cancel this B, for that AN minus A, I have chosen particularly. So this Bn, modulus of Bn is greater than or equal to small, and 1 upon Bn is less than or equal to 1 upon m2. So this I have chosen there. And here A is a common factor, A, Bn minus B, modulus of Bn into B. So again this m2, this to balance this, I have chosen Bn minus B is less than or equal to 2 1 upon m2, and to cancel this a, 1 upon a is taken. To cancel this b, in the numerator b is taken. So this is all how I have adjusted. What's my idea? Just to get epsilon by 2. The extra term should be cancelled. So here modulus of Bn is 1 by m2. 1 upon modulus of Bn is 1 by m2. To cancel this, An minus a is less than epsilon m2 by 2. Whereas Bn minus b, this Bn minus b is here modulus of a divided by modulus of Bn, and modulus of b is there. So Bn is m2. So a modulus of a divided by m2 into b, these terms get cancels. We have to cancel these terms. Therefore, I have chosen epsilon by 2 modulus of b into m2 divided by modulus of a. So only I left with epsilon by 2. So epsilon by 2 plus epsilon by 2 is epsilon. Therefore, the limit exists. So this is how I am getting the theorem. Go through the notes carefully. Any doubt, if you have, ask me. I will continue in the next class.